Look at the Earth's surface, and it appears entirely fixed. But on a geologic timescale, it is a dynamic system defined by continuous, highly organized deformation. For decades, elementary textbooks have taught a simple model to explain this deformation. They suggest that tectonic plates act like passive rafts, dragged along by the friction of massive convection currents churning deep within the Earth's mantle. The physics of this conveyor belt model do not add up. There is a layer of partially molten material at the base of the plates that acts as a lubricant, effectively decoupling the surface from the deeper mantle. If deep convection were the primary driver, the drag force at this boundary would actually resist plate movement rather than propel it. Tectonic plates function as active, gravity-driven engines, generating the kinetic energy required for their own movement. This map plots global earthquake epicenters in red against a dark surface relief. The seismic activity does not happen randomly. It concentrates in narrow, wriggling bands that precisely outline rigid plate boundaries, mapping exactly where kinetic energy is released under intense stress. To understand how the crust shifts and builds our landforms, we have to abandon the passive drift model. We need to analyze the specific force vectors that the plates themselves generate. This cross-section illustrates the critical rheological boundary of the Earth's outer layers. At the top is the lithosphere, a cold, rigid shell that loses heat through direct conduction. Immediately below it lies the asthenosphere, a hotter, weaker layer that loses heat through convection. Because the asthenosphere behaves as a viscoelastic fluid, it yields easily to stress. This structural weakness allows the rigid lithosphere above to shear off and slide laterally, moving independently of any deeper mantle currents. The life cycle of this lateral movement begins at divergent boundaries, known as mid-ocean ridges. Here, hot, buoyant melt from the asthenosphere rises to the surface to form new oceanic lithosphere. The immense heat and buoyancy create a distinct topographic peak at the spreading center. As new material continuously erupts, it pushes the older crust outward. Over millions of years, as this oceanic lithosphere spreads laterally away from the ridge, it cools, structurally thickens, and progressively increases in density. This cooling process creates a physical slope extending downward from the elevated ridge. Gravity acts continuously on this topographic gradient. The dense, cooling rock simply slides outward and downward, generating a lateral force known as ridge push. Gravitational sliding pushes the plates apart and initiates movement. But when geophysicists calculate the magnitude of this force, the math falls short. The ridge push factor alone lacks the required energy to propel the major oceanic plates at their observed speeds. We have to look at the other end of the cycle to find the missing energy. Far from the spreading ridges, at convergent boundaries, the oldest and most thermally mature oceanic crust eventually meets another plate. By the time it arrives at this juncture, the oceanic lithosphere has been radiating heat into space for tens of millions of years. It reaches a critical density tipping point, becoming significantly heavier than the hot asthenosphere it rests upon. Look at this cross-section of a subduction zone. The cold, dense plate bends and sinks into the mantle under its own weight. As this submerged section, the slab, plunges downward, it exerts a massive tensional pull on the rest of the trailing plate. This force is called slab pull. When modeled physically, the downward acceleration of this sinking mass generates a force nearly an order of magnitude larger than ridge push. Global plate velocity data confirms this mechanical hierarchy. Plates composed primarily of oceanic lithosphere that are attached to subducting slabs, like the Pacific Plate, travel at speeds of 7 to 10 centimeters per year. Plates lacking long subducting boundaries, like the Eurasian Plate, crawl at just 1 to 3 centimeters per year. The negative buoyancy of cold rock pulling the crust into the mantle dictates the primary velocity of the global tectonic system. Subduction continuously recycles oceanic crust, but this raises a mechanical question. What happens to the Earth's surface when a subduction zone completely consumes the oceanic basin between two landmasses? This map of the Pacific Ring of Fire illustrates the first consequence, known as activation orogeny. As the dense oceanic slab sinks, it grinds against the overriding plate. This massive frictional interaction, combined with fluids released from the descending rock, melts the upper mantle. This produces long, narrow belts of intense crustal thickening and active volcanic arcs. But the system hits a mechanical limit when continental crust arrives at the trench. Unlike dense basaltic ocean floor, continental rock is rich in lighter elements like silica and aluminum. It is highly buoyant, making it physically impossible to subduct deep into the mantle. When two buoyant continental margins collide, the result is indentation tectonics. This diagram maps the drift of the Indian landmass as it migrated north and slammed into Eurasia. With neither side able to sink, the continental crust underwent extreme horizontal shortening and vertical thickening. The deeply stacked rock then rebounded isostatically, lifting the Himalayas into the sky. The architecture of the Earth's surface is determined entirely by the internal density of the colliding plates. Subductible rock yields fiery volcanic arcs, while buoyant rock yields towering mountain belts. These vector forces operate in a continuous, predictable loop known as the Wilson cycle. Over hundreds of millions of years, supercontinents fracture, oceanic basins are born, they expand, they subduct, and eventually close, causing the continents to collide once again. This map reveals the structural remnants left behind by this cycle on the western coast of North America. When subduction zones operate for extended periods, they scrape off islands, inactive ridges, and coral platforms that cannot sink. These pieces are plastered onto the active margin, creating an accretionary origin, a complex collage of dismembered ocean floor and exotic terrains. We can map this life cycle across the entire globe. The massive, continuous collision zone stretching from the Alps in the Mediterranean all the way to the Himalayas acts as a geologic cemetery. These mountain ranges contain the crumpled, non-subductible remnants of the ancient Tethys Ocean, which closed up and vanished millions of years ago. Analyzing plates as self-driving mechanical engines establishes the physical framework needed to trace the evolution of every mountain range and oceanic trench on Earth.